Assalamualaikum and good day to all of you. Hope you are in a great state of mind in this uncertain and crazy time, right? I'm going to start the first topic for this course. So the title is Kinetics and Modelling in Fermentation, all right? So I think you probably have some idea what does it mean by kinetics. And for modeling, you notice that I'm using 2L here. This is actually British spelling. I think you should use British spelling uh, in the scientific writing. So make it a practice. I know the one that in your teaching plan is a single L, right? That is a US spelling, right? Okay, so for introduction, we have the first term, kinetics, right? So kinetics means is the study of reaction rate. Reaction rate, right? It could means concentration over time, rate divided with time. Okay, so model by definition, it represents empirical objects. Empiricals means based on observation or experience rather than theory or pure logic. All right, represent empirical objects, phenomena, and physical processes in a logical and objective way to construct a formal system for which reality is the only interpretation. So I'm not sure all these all these words give you a clearer idea or make it more confusing. So in short, it's nothing. It just basically means to create usually just a mathematic equation that can represent a system. So in our case, the phenomena or the physical processes means the fermentation process. All right. So modeling, yeah, with the word adding ing, so meaning is the process. It's nothing but the process. So it's the by word. It means the method of choice for obtaining precise prediction. Okay, so this is just the terminology. All right. Uh, for more introduction, so bioprocess engineers frequently relied on modeling. Why? To aid their understanding of the evolution in biological system. The evolution means the changes in biological system during fermentation processes. So basically, to help them for understanding of the changes. Okay. Often, a biological theory will lead to mathematical formulation. And the validity of this theory is tested by comparing predicted responses with data from actual experiments. So this sentence basically explains a lot about the process of modeling, right? First, you have biological theory from fermentation. For example, biological theory, you're talking about the cell growth, cell accumulation in bioreactor, right? For example, the cell accumulation or in the bioreactor is equal to the cells uh, that are feeding in to the system minus the cells that are outflowing from the system, all right? Plus the cell that growth, right? The rate of cell that growth, and minus the cell, the dead cell, okay? The rate of cell death. So that is biological theory, right? How you get that? How you get this idea? Usually you can get this from experiment or simply by theory, right? Because experiment will generate theory, right? So from that, you convert it to mathematical equations, mathematic forms, all right? And after you get the equation, you have to test the validity, right? So testing the validity means comparing the predicted responses with the real data. Okay, so we will look into that, into this uh, in a real world scenario later. So accurate quantitative models, even for complex biological system, will lead to rational design, control, optimization, and simulation. So this is the purpose of model. I mean the mathematical model. What is the purpose? The use is number one, a rational design for design, control, optimization, and simulation. So in our course, we will look at optimization and simulation. All right. We're not going to look at design and control because this is more advanced. Okay. Then the function of biological model is to describe the metabolic reaction rates and their stoichiometry on the basis of present and past fermented conditions. So this is nothing, just the use of the model. All right. So the main difficulties for modeling are, the first one, to identify the most important factors that influence the growth process. Now, for example, in the case of fermentation, there are so many factors. So it's quite difficult to determine the most important factors, right? Right. And then the next difficulties, finding a suitable model structure for intracellular processes. So this is basically talking about the internal system. Say you have a cell, you have internal enzymatic system, concentration, and also meaning what happens or the parameters that are within the cell. So it's a bit hard to actually model them, right? Okay. Now you have two types of kinetic models. The first one you have structured, and the second one you have unstructured. All right. The most common one is unstructured. Is the one that we are going to use. So unstructured meaning simplistic take on cell as a uniform quantity without internal dynamics. So meaning the internal dynamics are not considered. So yeah, all right. So it considers no form of structure in the protoplasmic mass. We know in theory there's so many things happens in the protoplasmic mass, right? But for this model, we just kind of neglect uh, the internal dynamics, okay? So whose reaction rate depends only upon the condition in the liquid phase of the reactor. So meaning we just consider the external environment, okay, uh, upon the conditions, so meaning the conditions in a liquid phase, right? We don't consider what happened within the cell, okay? So only contain kinetics of growth, substrate uptake or utilization or consumption, and product formation. So there are three parameters that usually we consider, all right? So this unstructured model is adequate for many technological purposes and are sufficient in understanding fermentation processes. So if you, clear with these three kinetics, so it's quite enough already. All right. Another one, structured. Structured is actually more complicated because it takes into account the aspects of the cell components, such as concentration of metabolites, enzyme, lipids, and RNA. Right? For example, you're talking about you want to model cell growth, right? Suddenly you want to include how much DNA concentration will affect, how much is the enzyme will affect. So it's so complicated, okay? So ideally, models should be able to imitate the cell physiology, metabolism, and cell generation. Okay, this is basically general statement. The model is said to behave analogously to a cell changing its composition when responding to perturbation in the extracellular environment. So this is basically describing the model, which is considering, taking into account the internal dynamics. Okay, so for simplicity, we actually bother of covering or focusing on this unstructured model. Okay. Next, we have model variables, all right? Model variables, central to the development of any model is the definition of the components within biological system in terms of macroscopic variables, something that is at larger scale, something that is more measurable. Okay, so the components in this case it can be concentration of chemical substances. For example, you can say concentration of cell, concentration of product, concentration of substrate, right? Something that is macroscopic can be measured, all right? Amount of energy, temperature, right? So this can be the variables. Okay, we'll look at into the real mathematic variables soon. All right, so types of variables, okay? The category also is fall under macroscopic, right? Macroscopic variables. But then these are the type of the macroscopic variables, not microscopic. Microscopic meaning the one that in the cell, the internal dynamics, like enzyme concentration. But we are bordering the macroscopic variables only. All right, so there are so many types. There's 5 categories of the macroscopic variables. All right, we have state variables. All right, state variables, we have operating variables, we have stoichiometric parameters, we have kinetic parameters, and intermediate variables. So by definition, a model is a set of relationship between the variables of interest, right? Variables of interest, it could be any of these variables, x, s, p, rate, rate of cell death, rate of cell growth, etc. in the system being studied. Okay, so this sounds more understandable, right? For the definition of model. Another one, the one that we encountered before is this one. Yeah, it sounds more complicated, right? But I hope you get the idea by now, all right? So what is the difference between intermediate variables and kinetic parameters? So basically, you need an example to actually differentiate these categories. So the first question, intermediate variables versus kinetic parameters. Intermediate variables is something like rate of cell death. The symbol is Rx. RD, rate of cell growth, Rx. So these are intermediate variables. Rate of glucose consumption, right? Maybe, yeah. Kinetic parameters is the one like kinetics parameters, for example, like the specific growth rate, maximum specific growth rate, right? So I think you have probably learned this a bit in the fermentation technology class subject, right? So this is a time when you really take the opportunity to really learn and understand this topic very well, so that you can make use of the knowledge. All right. So kinetic parameters, example, specific growth rate, maximum specific growth rate, or mu max, right? This is mu. Doubling time, right? Yield coefficient, and etc. Okay, we look at other example, operating variables, just like your feeding rate, right? Yeah, state variables, the three, X, cell concentration, S, substrate concentration, and P, product concentration. Stoichiometric parameters is the one that give you the numerical values in the equation, usually in the chemical equation, right? That show the correlation, right? Okay, then this is more detailed explanation on the variables. You have state variables, define the state of the process, and there is one for each extensive property, for examples. So these are the example, cell concentration, XV viable, non-viable cell, XD. This is big X, capital X. This is subscript. Okay, S, P, S is substrate concentration, but take note there is word limiting. Limiting means the most important substrate for growth, right? That is growth limiting. Okay, so P, product concentration. Operating variables, I think from the name itself you can guess, is something that can be controlled by the engineer or by the operator of the fermentation. So operating variables, these are variables, the values of which can be set by the operator of the process. For example, you have dilution rate, you have volumetric feed flow rate. So these are operating conditions, right? Operating variables, okay? So intermediate variables is these are all the volumetric rates, right? Meaning it's based on volume, which can all be expressed in terms of the state variables listed above. So intermediate variables will include state variables, right? For example, this Rx, rate of cell growth, Rd, rate of cell death. This one is Rsx, rate of substrate utilized by cell. This one is rate of substrate utilized for RSM for maintenance. Rate of substrate utilized for product formation, RSP, and RP, rate of product formation. Okay, so look at these intermediate variables in which the state variables are also included, right? P, you have S, you have X, right? Which can all be expressed in terms of the state variables listed above. Okay. Balance equation. So this is very interesting because this is actually the basis of mathematical model construction. So the basis of macroscopic description is the balance equation. So how you actually generate all this mathematical equation or model is based on balance equation. I think you will learn mass balance in the subject bioprocess engineering as well, isn't it? So for each of extensive quantity, right, a quantity which is additive with respect to parts of the whole system, a balance equation, right, whether it is mass or energy, in our case we border mass, you know, not so much in energy, can be derived. And its general structure always takes on the form of, right? So I'm not sure this sentence are making you confused or not, but I think you should just try to digest one by one, right? So it's nothing but the balance equation form is this. This is something that you have to remember, right? It's based on this. Accumulation equal to transport plus conversion. Try to think logically. Accumulation accumulation in the fermentation, in the fermenter or bioreactor is equal to transport, right? Transport meaning the one that going in and the one going out, right? And conversion meaning the one that is formed in the bioreactor. For example, the cell growth, right? And conversion, maybe they're also the one that exists but then gone because of death or degrade or something. So this is basically what it means. Whatever accumulate in a bioreactor is depending on the one that is being transported in and out, and also the one that is being formed or degraded, which is called conversion. Okay, so this is the basis, very important. Okay, so balance equation, then continue on that. Here, two types of mechanism are distinguished by which the total amount of an extensive quantity in system can vary. The first one is transport. Yeah, I know the sentence very bit challenging to understand, right? But don't worry. Just take note that the two elements that contribute to the accumulation. The first one is transport, and the second one is the conversion. All right, nothing. Okay, next we move. The balance equation results in a so-called state equation of the model. What does it mean by state equation? Which describes the time dependence of the state variables of the system. So to understand this sentence is nothing but you just have to look at the real equations. For example, this. All right, this is what actually it means. Okay. Don't worry about that. We come to this slowly. All right. Since we are talking about fermentation, so you have to identify the state variables first. So in these slides, you can see the important or the most common state variables in a fermentation process. We also have operating variables, right? So can you identify them, right? I think by this point, the expectation is everyone can draw this and list these state variables, right? So, of course, you have these three. As I told you, the state variables, right? X, S, and P. But take note now, we suddenly have this subscript I, right? And then we have the subscript O. I meaning inflowing, yeah? Inflowing. Whatever that is being added to the system after the fermentation. For example, in the case of fat batch fermentation or in the case of continuous mode fermentation, you don't have this in a batch, right? For batch fermentation, all this is equal to 0, okay? Then you have the one that outflowing from the system, okay? Therefore, you have this O, all right? And then the one that is the bioreactor itself. For this one, there is no I or O, all right? Okay. So other parameters beside the state variable, you have this F, all right? This is operating variables. This one as well, outflowing, right? Liquid flow. And then we also have V. V is the volume in the bioreactor. So I expect everybody uh, able to draw these state variables, okay? And also you can take note on the unit for each of the state variables, right? Cell concentration, gram per liter, and the rest, anything about concentration are usually gram per liter. Volume, you can use liter, a standard unit. While for bulk liquid flow is usually is the concentrations over time, okay? Okay, use gram and liter and also hour. All right, next slide. Okay, this is the general model, the general mathematical model or mathematical equations that describe the state accumulation of state in the bioreactor. All right, there are basically three uh, important states, main state, right? State variable in the system, which is based, the first one based on biomass, and then the second substrate, and the third one product. And for the last one, number 4, this one is for volume. Okay. These are the intermediate variables. All right. You have like small r and subscript x, right? And then continue until rate of cell death, right? So rate of self growth, rate of substrate consumption or utilization. Please take note of the unit, guys. Rate of product formation (RP) and rate of cell death or deactivation, or you can use any words that you like. Okay. So look at this model. All right. So basically you have, can you identify the state? So these are the state variables, right? State variables X, the V, you have also X here and V here. This is intermediate, all right? You have intermediate, this one also, all right? So let's look at, how you actually come to this, all right? So this is biomass balance. So as shown here, this is basically the basis The balance equation is the basis of to construct the model. Rate of accumulation equal to rate input minus rate output. Is this correct? Is this correct, guys? No, this is not correct, because rate accumulation not only include rate of transport, it must also include rate of what? Conversion. Right? It must also include rate of conversion, right? So this is there's some missing here. Okay. All right. So let's say we focus on the biomass or cell concentration. Rate of cell accumulated in a bioreactor is equal to the rate of cell being added minus the cell that is outflowing, right? That is going out from the system, all right? Plus the rate of cell that is formed minus the rate of cell death, right? Okay, so for this first part, right, this is actually the rate of input, the cell added, minus the rate of cell going out, okay, and minus the cell that is being formed in the system, okay, minus the rate of cell death in the system. So all this you get equal to the rate of cell accumulation in the bioreactor. You should try to work on it by yourself. All right. Sometimes you need to check the unit as well. You have to check what is the unit of this and what is the unit of this. These two combined. Well, what will be the unit, and is the unit going to be balanced from the left to the right side, right? You can do that, right? All right. So this is actually not very hard to draw. You should try and practice to draw until you can remember. You don't have to memorize for this, okay? All right. Next, this is basically the adjustment of the uh, operating variables to the mode of fermentation. For example, as I told you, for batch fermentation, there is no inflowing and there is no outflowing, and therefore this value is equal to 0, right? So if you try to use this general form of equation, if you try to adjust it to batch mode fermentation, this part will be gone and this part will be gone. So it becomes simpler, okay, for fat batch and continuous. All right. Okay. So let's look at kinetic models. So what does it mean by kinetic model? So it's nothing from the name itself. I think you can guess. It's basically it's about fermentation. So it's about a mathematic equations that has kinetic parameters as the variables in the equation. So that's what it means. Okay. So in terms of microbial culture inside the fermenter, complementing the balance models are related kinetic equations. All right. For example, if you look at this general form of equation, you can actually expand these intermediate variables to include the kinetics variables. All right. There's a reason why these are called intermediate variable, because they can be expanded to include the kinetic parameters like the mu max, what else? Yeah, doubling time, yield coefficient, etc. So, all right, there are several, but the most important one is these three. We are going to cover these three, okay, only. For kinetics equations, they are the ones for rate of cell growth and death, substrate consumption, product formation. Okay, all these three methods. And the rest, which we are not going to cover, but then you can just extra information for you. The equation representing rate of heat and mass transfer, system property changes, equilibrium relationship, and also process control. This is even more advanced and rather complex. Okay. Now we come to this modeling procedure. So modeling procedure, how basically people do modeling, right? Just now we have looked at how the mathematical model is constructed. What is the basis of making mathematic models? But now we are talking about the whole process of procedures of modeling, right? How you actually start the modeling, say fermentation, how you start the whole process until the end of the day, what you actually get, what is the standard procedures. So modeling procedures is a combination of these relationships. Combination of this relationship provides a basis for the quantitative description of the process and made up of basic mathematical model. Can be only few equations to very complex. So these are the models, right? Okay, modeling procedures. The first step is basically you define the bioprocess. All right, define the bioprocess. Say fermentation. That is a bit general, maybe. And later you go for specifically say the cell accumulation in the bioreactor. All right, and then you come to that. The cell accumulation in the rate of accumulation in the bioreactor is equal to the rate of cell form minus the rate of cell death minus the rate of cell that is being feeded in uh, minus the outflowing cell, right? That is basically the bioprocess or the specific process they're looking at. And then that process available theory must then be expressed in mathematical terms, meaning you try to convert it in a mathematic forms. All right, say this one, right? Okay, and then having developed the models, the equation are to be solved. You need to solve this equation. Okay, what does it mean by solve? All right, later solve. Later you will come to this in the practical session. So we will get a clearer picture as we progress. Okay, and then the computer prediction must be checked, and if necessary, the model is to be revised. So after you solve that models, you get a data, right? You need to verify whether the data is consistent with the experimental value or not, right? So in order for the prediction to be or the model to be valid, it should be uh, comparable to the data from the real experiment. Okay, so this is basically a very important diagram, right? It's not very hard for you to understand. You can understand it by now, even though you are not really doing the modeling process, but you should understand it now. So I think I'm not going to read on all these word text sentences, right? So I'm going to describe in general on the diagram. So let's say we start with a process, as I mentioned to you, say fermentation. You can be more specific, rate of cell accumulation in the bioreactor, for example. So you know that maybe in the process, I mean specific, you need to generate the physical model, or you call it state model, is the one in the form of words that describe the system. For example, as I mentioned earlier, you're talking about the cell accumulation in the bioreactor. You have to describe it up until the final what rate of cell death, right? In the long equations. So how you actually get this physical model is One is simply by theory, but number two is, of course, contributed from your own experiment. You have like preliminary experiment, and then you come up with a theory, all right, with a theory, with a concept, and then you change it into a physical model, all right, and then that physical model, all right, or that state model, that idea concept is converted to mathematical model, okay, with mathematical model, and then you try to solve that model using computer data, right? This is the part where you might lack of idea on what is this all about, but we'll come to this later, okay? And based on the computer data, all right, you get you compare data obtained with the one that you obtain from experiment, right? You have to compare the data. So if the data match, so meaning the model is verified and established. But if the data is not matched, the both of the data is not matched, so you have to revise again the physical model or this concept, right? Conceptual models, and also the mathematical model, obviously. So please take note of the direction of the arrow here, right? It can go up and down, so meaning is the kind of like can be readjusted, okay? So if you get if the model match with the experiment data, that means good. And then you can use that mathematical equation for the purpose of design, optimizations, control, yeah. And another one's the simulation, right? So actually, I think we're going to bother only optimizations, right? So in other words, if you want to do optimization, you need the mathematical equations. Okay, all right. Okay, this is a slide that's trying to explain on the model computation, right? Model computation is just a sum of very general. Maybe you should just read it, and I understand that it's very hard to really understand what does it mean by computer model computations at this point. Okay, so model computation, this one is a model competition. So talking about the software that can be used to solve the model. You have Excel, you have GraphPad Prism, you have Sigma Plot, Curve Expert, MATLAB, dynamic modeler. So this model computations is for basically is explaining a little bit on the solving of the model, right? For this part, mathematical model, you solve it, you get that, you solve it here, and then to get the data. So what actually it means by this solving the model, right? This one, having developed a model, the equations are to be solved. What do you mean by solving the equations? So this is a part that you come to really understand during the practical. All right. So, but now you can have a look on the text first, right? Maybe to give you a little bit of idea on what is this model computations is all about. Okay. I think this is the last slide, and I think we can stop here now. All right, and that's all for today. And hope you have gained something. All right, till we meet again in the next presentation. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good day.